Hello, this is Dr. Wang again. In this video, I would like to work a numerical example how to set up and actually carry out a hypothesis testing of a single mean. So here it goes. Going right to the example here. I have a river that's polluted with some contaminants. And I like to know what the actual average over the entire lake or river is, but I only do a sampling of n equal to 12 at 12 spots. That's all I can afford. By the way, where in the 12 do you do the sampling is another art or science to itself. There's a whole study on how do you make sure you collect do the sampling that representative of the entire population, not just any 12, but it has to be correctly designed. Anyway, you find the pollution level, the mean of the 12 pollution level is 35 parts per million. We measure that part of the coliform, which is the bad bacteria things. Let's just say, with a sample standard deviation of 4.3 parts per million, let's just say. So here is our sampling result. And suppose the EPA says you have to reduce this to less than 32. Let's just suppose. Now, even though I have 35, but my standard deviation is 4, so 35 minus 4 is 31. So I could actually be less than 32. So I want to go ahead and test the hypothesis. Remember the null hypothesis equality? So I want to go ahead and set up the null hypothesis, because I have ulterior motives. I want to see if it can be 32, because that's the EPA standard. So I want to test if my mu can actually be 32 parts per million. That's my mu null. Now, what is our alternate hypothesis? Well, do I want to test mu not equal to 32? No, not really. I wanted to see if, since my sampling result 35, I wanted to see whether it's actual mu, which I never know, but I can test for, is larger than 32. First of all, this is 35. I can only test larger than. You cannot test smaller than, unless this sampling result is less than the one you're testing. So this is actually my mu null. This is the one I'm actually testing. So you're going to compute something. If what you compute says you have to accept this, then you have to reject this. If your computer result says you have to reject this, then you have to accept this, larger than 32. Now suppose you say, how much larger than 32? Well, you can test another one. Can mu be equal to 33? If it says, no, it's actually, you have to accept larger than 30. You keep testing until it says, yes, it could be as much as that. But I want to tell you up front right now, this is my engineering bias, and I hope to rub it on you, I hope to brainwash you, that hypothesis testing is one-point testing, either yes or no. You accept this, you reject this, or you reject this, accept this. It does not give you the overall where about your actual mean, population mean is. So I personally prefer the confidence interval give you, at least it's this big, at most it's big, somewhere along here. This gives you yes or no. But why is this so popular? Why is you hear it used all over the industry, engineering firm? Because, I'm sorry, a lot of people are not very savvy in interpreting statistical results. This is a binary test. Either you accept yes or no. People like that. It's clear cut. And so you say, hey, let me give you a confidence interval. What the heck is the confidence interval? I better have some kind of expert to help me to interpret. So they usually don't like that. But I want you to help you educate your company culture to actually use confidence interval in conjunction with this, not just to use hypothesis testing alone. Okay, that's my aside. So I did my soapbox thing. So here, continue on. So what do we calculate? We calculate this thing right here you see. This is called a test statistic. Don't worry about the name. The name could be Mickey. This is Mickey. But anyway, this is what you have to know. How do you know this is what you calculate? It's listed in every standard statistics textbook. This is called a test statistic for population mean. This is your X bar. This is the number you calculate. So here we're going to do mu naught. This is the number you're testing. Here is 32. This is S, the sample standard deviation. This is the N. Again, you see how this N appears here. Okay, so let's go ahead and calculate that. Let's see what we get. Now, do we calculate Z or T? Our sample size is 12. So remember, 30 is a breakpoint, so we cannot really use this. We're going to calculate T. So let's go ahead and we have to use a T statistic. So T is X bar, which is 35, minus the thing I'm testing right here, 32, divided by S, which is 4.3 divided by square root of n 12. Anyway, you carry this. I hope I did this already. Yes, I did. 2.42. Okay, what do you do with this? You circle that. Now, this is t, statistic. That means this whole distribution of this number is governed by the t, the student t distribution. As you recall, I introduced a t table, which has to do with the degree of freedom. Here we have n equal to 12, I mean. The degree of freedom, which is new, is for a single population, is always n minus 1, which is 12 minus 1, which is 11. So in your t table, you look under new equal to 11, and we're doing one-tailed test, larger. We go to over here. The number we are interested in, we want to know the t value that leaves the entire 5%. We're doing one tail, we're doing 95%. If they don't tell you what level of confidence, always assume it's 95%. You won't go wrong. We want to leave the entire 5% area to the right here. We want to find that t value that leaves 5% at the degree of freedom of 11. You go to your t table, you look for that t value, which I did already, and this value is equal to 1.796. Remember that I'm going to use this a lot. So here is the number, so this is the number right here. Now remember what I said before. If your computed statistic lies to the left, it's the OK region. Everything here, if you come, is OK region. If it lies to the right of your t-table right here, not OK. I don't want to use a blue because blue usually means OK, but I don't have anything. I use not OK. Forbidden. I use forbidden region. Your computer cannot be here. If here, you reject. Here means you reject H and R. It can't be true. This whatever hypothesis here, this cannot be true. You have to accept that. So here comes the moment of truth. What do we have? This is 2.42, and I'm comparing with this. It's over here. It's right here, 2.42. Right here, which is larger than this critical, we call this critical value. By the way, this, don't worry about so many terminology unless you want to be really appear like this. Anyway, this is called critical value. In case you read communication, they'll say the critical value for this testing is. So that's what it means. You compare this number, you compute with critical value. Since, you say since 2.42 is larger than the critical value of 1.796, therefore, this is called therefore, it follows that you reject H0 and accept H1. Now, you do not put this here in your report. Your management say what? Don't speak Greek to me. Put that in plain old English. So what is a plain old English for that? I'm going to write down here. You're going to remember this. Always put this in your report to upper management unless you're publishing a scientific paper, journal, then you use all these terminologies. So what does reject this accept means me? It's over here, 32, ppm, pollution, larger. You say sampling result, data, I just say data. The only data you have is sampling data. Data does not support, sorry, gotta prime this, does not support the claim or the hypothesis that the pollution level is at 32 ppm, parts per million. It rather supports the claim that it is larger than, of course you put the word larger, 32 parts per million. What now? Can't see it. Oh, can't see it. Well, anyway, I'm going to repeat again. Based on the results, since you reject this, you have to accept it. You say data supports the claim that the entire population, the actual pollution level is larger than 32 parts per million. Suppose you manage to say, how much larger? Is it 34 Well, I don't know. I got to do another testing. So how do you do testing the next round? Because I don't want to know just larger. I need really to know how much. So you put 34 here. You say, can it still be larger than 30? You see here 35? So you put it at 34. You go ahead and do the whole thing, except instead of being 32 over here, you're going to put 34. As you can see, this number becomes smaller. Instead of 3, it's the 1. This becomes smaller. What does smaller mean? It pushes the number to the left until it passes through this forbidden region, push here to be acceptable. You're going to keep rejecting the null if it lies here. So it starts here, going to move closer, closer, closer as you increase this number until it crosses here, then you're going to accept this number. Now, what is that number that upon which you're going to accept? It turns out it corresponds to the upper level of your confidence level. So why don't you just go ahead and compute the confidence level to begin with? It gives you the entire range where your true mean is instead of keep doing a point by point. Because if you put 30, can you put actually 37 here? Yes, you can. You can actually say, can I test 37? Then here it has to be less than 37. You see this is 35? You can do such a testing. If I accept, yes, you can still accept 37. Wow, EPA is you're really way off mark. So, okay, so next example, I'll give you a test of two means. Hypothesis and two means.